Optional extension. Here we go. So suppose we reran this notebook hundreds of times with different seeds. What's the expected value of the validation loss? So we're going to look at how is y true constructed. We made our y true way up here by taking 4x minus 1 plus noise. So this noise is going to be a fundamental limit on how accurately we can predict y from x, because noise was random and has nothing to do with x. So even a perfect model, if we modeled this part of the model perfectly, we'd still have this noise to contend with. So what effect does this noise have on our accuracy? So I want to point out something numerically first, and then we'll see how it works in math. So notice when we got a good fit, our training loss and validation loss were both about 0.02, which had a square root of 0.155. Let's look at what's the standard deviation of our noise. 0.1415. What's the variance of our noise? 0.02. Does that ring a bell? In fact, remember that standard deviation squared is variance. Exactly the same here. So the amount of error that we can't get rid of is the variance of the noise. Now, what was this noise? Well, it was a, probably need to, yeah. Let me just get the first feature out of it. Let me make sure I'm doing it right. It's a tensor, and maybe I just need to numpy it, and then hist that. Yeah, there we go. So this is a uniform distribution between 0 and 0.5. So what's the variance of a uniform distribution on 0 to 0.5? Well, here we can go over to the Wikipedia page on the uniform distribution. And here we got A is 0, B is 0.5. We've got a uniform density there. And we can look up what the variance is, or you can compute this. It's a slightly annoying integral, but there's also some clever ways around that. But you could, for now, just look it up. So the variance depends on b minus a squared. So it's how big this interval is, b minus a. Here we had 0.5 minus 0, so 0.5. So we're going to have 0.5 squared, 1/12 times 0.5 squared. So let's see if that matches up with our value here. So 0.5 squared is just 0.25. So 0.25 over 12, 0.021. 0.021. There it is. So that we determined by just looking at the properties of noise as a random variate. So if we did a bunch of different random seeds, we'd just get different random values for the noise, and their expected variance would be this. And so if we assume that our model perfectly learned the weights and biases, then this is what error we'd get. Now, it turns out in order to compute this expected value, I don't think we need this assumption. I think we should be able to just say that this is, since our model was exactly of the right family, I think it simplifies that all of our variance comes from here. Now, if we had, so this is basically the fundamental variance of the model. Because our model itself has zero bias, we've got exactly the right kind of model. Our NN linear should be able to exactly model all the aspects of this, of our real data. This is exactly a linear model of the right dimensionality. So our model has zero overall bias. but we still have fundamental variance due to the noise in the data. We're going to learn more complex models. And for more complex data, even this simple model has a lot of bias. So we'll talk more about these different considerations later, but I wanted to give you a little preview of how there can be certain kinds of just unmitigated bias in or unmitigated variance in the data. We're never going to be able to do better than this as our validation variance on average.